No, I mean like along the centroid, as far out from the center as possible, that's where it's
Yeah,
going to
yeah,
crack.
you are absolutely. So the failure can be either at the top, at the bottom, due to normal. Yes or no?
No, that's not what I meant, but I think I'm confused. Where is P in the cross section?
So if I draw transformation, this is your X and this is your Y. And in this case, the cross section, this is your Y and this is your Z. This is rotation about your X. So this is the cross section view. Sorry.
So would the P just be up top?
Yep. Right. So if we're going to draw, right? If we're going to draw the normal stress distribution, where is the normal stress highest? At the centroid or furthest away from the centroid? Anyone?
Oh, furthest away.
There you go. So if normal stress, it will feel at the most extreme ends, yes or no? Right? Right? So if we were to if we were to go back to our introduction, okay, if we were to go back to our introduction, right? If we were to go back to our introduction, right? So we have drawn, right? You guys now know this already, right? We know, so this is normal stress and shear stress, and this is the Y, right? So now you know, right? The normal stress distribution, the highest is at the what? Extreme. Yes, right? Whereas the shear, the highest is going to be at the where? At the center, right? So where we are now in the analysis is you guys are capable of identify what is the normal stress and the shearing stress. Okay, the next time after we finish shearing stress, what we're going to do is we're going to combine the normal stress and shear stress together using 3D mold circle. Okay, so you guys are progressing already. You can see how far you are going, and we're at week what? Week 5, almost halfway, I think. Okay, yes. Okay, so there's just a map on where we are in our series of lecture. Right, so now this is mode number 3. Now, for this case, we're not going to combine normal stress and shear stress yet. Okay, for this case, we are just going to make it simple. Okay, Connor, you have something to say, Connor? You okay?
Oh, nothing. I just realized my mic was on. Sorry.
Okay, so I saw you blinking. Okay, right. So now we are going to do mode 1 of failure. Okay, so we're going to look at mode 1 of failure. But before that, the question asks us, we are going to determine P. Okay, we're going to determine P. So we are going to go into mode 1 of failure.
Wait, sorry. Wasn't P given to us as 8 KSI?
No, P we don't know. We have to find P. If you look at the
Oh,
question, we are tasked to find what is P. Okay, so now let's do mode 1. So we're going to find failure is due to the fastener. Now, anything you don't understand, you just ask. Okay, this is now live. Okay, we are not watching videos. Unlike the videos, there are other previous student asking question, and you can get the information. Now you have to ask. Okay, so now let's look at the shear failure due to the fastener. So the formula we are going to apply is Q is equal to the force the fastener could resist divide by spacing of the fastener Okay, so this will be equal to, so we are given under single shear is 600. Okay, so this is under single shear. All right, and then you have to multiply the 2. Multiply the 2 down here is not because you have up and down. This is because it's under what? Double shear configuration. Right? Then we divide by the spacing, which is equal to 6 inches. Okay, so we get this equals to 600 times 2 divide by, so it's equal to 200 pounds per inch. Okay, now are you okay with why double shear is times 2? Okay, if not, if you look at the previous where did we do single shear, double shear? Sorry, not here. So if we look at single shear and double shear, so in single shear the force is P equal to tau multiplied by A, right? Double shear, the load P now is equal to 2 shear multiplied by A. This is where the 2 comes in. Are we clear? Okay, makes sense, right? Okay, so now we have this formula. Okay, we found our shear flow due to the nail, and the next thing is we are going to relate this to be our VQ divided by I. Okay, in this class I don't want to waste time. Okay, second moment of area, you guys are expert in looking for it already, so I'm going to just say I is equal to 29.02 inch to power 4. I'm just going to be direct. Okay, this 29.02 inch to power 4. Okay, so the next, so now we're going to, we know I, right? Next, we don't know what is V yet, and we don't know what is Q yet. Okay, let me tell you this. V is the most easy. Okay, I repeat again. V is the most easy. So next, we're going to construct FBD. Any idea what does FBD means? Anyone? Anyone?
I thought it was free body diagram, but I don't know what the FB is
That's the
for.
last one. How about the first FB?
Force balance?
Huh?
Force balance?
Wow, God. Jasmine, you're going to have heat transfer later on. What are you doing here, okay?
I don't know. It's okay.
Yeah, it's comedy, right?
I'm in denial.
It is known as freaking big free body diagram. Okay, so when you draw free body diagram, don't draw a small one. Draw a big one. The bigger the free body diagram is better, so we are more clear with an analysis. Okay, so we FBD stands for freaking big free body diagram. So from here, oh Lord, I got my, some of you were in 3C with me, and G, I got hammered again. The evaluation was not bad, not the best, not bad. But you all wrote that I have so much comedy in class, you know. It's okay, it's okay. Anyway, humor gets us along throughout the lockdown. Okay, so this is where we have AY over here. This is BY. Unfortunately, this is my second time I teach most of you. I have no more jokes, okay? Then I will ask you, what do you call an exploding monkey again? Anyone? So this is our P. So this is our free body diagram. And then this is our transformation. Okay. X, Y, rotation about Z. Okay. So we're going to base on static analysis. Right, based on static analysis, we can form an equation where summation about forces in the y direction is equal to 0. And we know that this is AY plus by BY. Hey, my B don't look like a proper B, man. Wake up, UG. Minus P is equal to 0. And then we say note. We know that AY is equal to BY due to symmetrical loading and geometry. It has to be symmetrical loading and geometry, yeah? Then you can make this assumption. So therefore, with that, we can say 2AY is equal to P, AY is equal to P over 2, okay? And this is equal to BY. So very quickly, so from here, okay, from here, right, we can very quickly sketch our shear force and bending moment diagram. Okay, so I will move to the next page. I believe you guys, can I move or you guys are still copying? Are we okay? I have no one stopping me. Okay, I'll go to the next page. So I'm going to copy this diagram still. So looking at that diagram, okay. So next we are going to construct our shear force and bending moment. Might as well do this now because we need our bending moment later on, right? We need the bending moment later on. So we are going to have, okay, so we know our specific distance. Okay, so shear force, I'm going to draw. Okay, so this is our X distance. Then we have our Y, right? So we have our 0. So we are given that the force will apply at P. Okay, so P, well, so this is our 48 inches. It's in feet. So how do I get 48 is equal to 4 multiplied by 12. And then the next one, 245, the next one, this is where my 96 inches goes to. Okay, so it's simply supported. So we have 0.5 P, right? So it's going to go horizontal. It's going to come down by over here. So over here we have minus 0.5 P, driving towards the horizontal, going back up. Okay, so from here, sorry, the y-axis. So from here, we know that our Vmax is equal to 0.5 P for this case. Okay, and then from here, we can construct our shear force diagram. Sorry, bending moment diagram. And the bending moment diagram, I'm going to focus on the positive only. Any idea why I only focus on the positive on the bending moment? Any idea, anyone?
Because the positive should be equal to the negative, and it's just the magnitude you need to worry about right now.
No, but why? That is not. We have to be careful with that, okay? But why do I decide just to focus on the positive?
Is it because the question gave sigma allowable as a positive number?
No. And what's on the background? You watching Miriam? You watching soccer or something like that? Okay, no. Right. I'll tell you. So if I'm teaching this now myself, so positive bending means based on deformation, right? When positive bending means the deformation pattern, this is deformation. This is how the structure will deform, okay? It's going to be smiling face deform. Negative deformation is going to be what? Set face deform. So if we look at the structure now, our structure will deform this way, yes or no? Exaggerated, right? So smiling face or set face? Smiling face. So that is why I'm being thrifty, not cheap, okay? Thrifty. I use the deformation pattern, the space for the negative to be very small. Okay. So we know that this is going to be a positive slope, right? So